Howdy. The purpose of this video is to describe families of directions and planes. Now, what are families and why do I care about them? Families are a set of directions or planes that are totally crystallographically equivalent. What I mean by that is that there's no way to distinguish between one direction and another direction in that family unless I've established a particular set of coordination axes. Now, why do we care about them? It turns out that the physical properties of materials, of single crystals, the symmetry of those properties is dependent on the symmetry of the lattice. And so there might be a set of directions where I can measure identical properties, and that's because the lattice is symmetric in that direction. So here's just a quick example. This is graphite. So graphite is composed of hexagonal sheets of carbon. And it turns out if you measure certain properties, including thermal conductivity, you get much lower values out of plane, so this is out of plane, versus in plane. And specifically, if I were to look in plane, if I measure in certain directions, I'll get exactly the same value because the structure is crystallographically identical in those directions. If I measure in some other direction in plane, I might get a slightly different value. But the important thing here to remember is that the physical properties of single crystals are dependent on the symmetry of that lattice. Okay, so let's think about an example. Let's think about a square lattice. So we're just thinking in 2 dimensions initially. Say I wanted to measure some property, and for this example, let's measure it vertically up and down. So let's think about maybe electrical conductivity. So I can make a graph and plot the electrical conductivity of that point here. So let's do the same thing, but let's rotate the lattice again. Now I'm still measuring in the same original orientation. So all that has changed is the rotation angle of that lattice. And in this case, maybe the electrical conductivity has decreased a little bit. And I can measure that again and again and keep rotating it each time. And I'm going to get a slightly different value for that property because the structure of this lattice is different in those cases. And so you'll see I went from originally having a very close spacing between neighboring lattice points to something where I had a much greater spacing between the lattice points. So maybe that's why I'm seeing a change in the physical properties. Okay, what happens as we keep rotating the lattice? It happens that as I rotate that lattice all the way back to an angle of 90 degrees now, I'm going to measure the same exact value as I did originally for the electrical conductivity. This is because the structure, as I've shown it here, is entirely equivalent to the structure rotated by 90 degrees. So let's look at that again. Here's the original structure. After I rotate it 90 degrees, I see the same exact thing. And that's what I mean by equivalent directions, right? This lattice looks the same in this direction as it does in this direction. So if I kept doing this, if I kept rotating, I would see this same pattern repeated. So this would be 180 degrees, and it would keep repeating. And in this case, that's because I have this fourfold symmetry. Every time I rotate 90 degrees, it looks exactly the same. So that's what a family of directions is. These are, let's clearly indicate these, the 4 directions that would be equivalent in this case are these 4 directions. So they all look exactly identical crystallographically. Another way to think about this is that if I start off with a system, it doesn't have an XY coordinate axis on it yet. We have yet to discover a single crystal in nature that has a XY axis clearly labeled on it. So if, for example, I asked you to draw the 1, 0 direction on this lattice, there are only 2 indices because it's a 2-dimensional lattice, you would first have to define your coordinate system. So maybe you would choose U1 and U2, and given that coordinate system, you would draw the 1, 0 direction, it's this direction. Now, if I ask somebody else to do the same thing, maybe they would define it this way. And in that case, the 1, 0 direction is that direction. So until we identify a coordinate system, so the two principal lattice vectors in this case, we can't say which way the 1, 0 direction is. Remember, all of the set of family of directions are those that are totally crystallographically equivalent. So if I'm sitting at a lattice point and I look out, this direction looks the same as that direction, the same as that direction, the same as that direction. If I were to notate these families given this coordinate system, this would be 1, 0, 0, 1, bar 1, 0, 0, bar 1. And I would say the family of directions is 1, 0. So when we write families of directions, we use these angular brackets. Now, the same exact thing is true for families of planes. So for example, if we think about a simple cubic lattice, that's a lattice that has a lattice point at the corner of each cube. The closest packed planes, the planes with the highest atomic density in this lattice, are the 1, 0, 0 family of planes. So when I'm talking about a family of planes, I denote it with the squiggly brackets. But again, there's a number of different planes that are totally equivalent. So this set of planes is totally equivalent to this set of planes and to this set of planes as well. So cubic systems are nice because if you want to say what are the family of directions or planes in that cubic system, you can reorder any of the indices and you can switch them from positive to negative. So the 6 planes in the 1, 0, 0 family of planes would be the 6 that I can obtain just by reordering the arrangement of the indices and switching any of them from positive to negative. And that's a shortcut, but that only works for cubic systems. Okay, so just in review, we've talked about families of directions and planes. We talked about notation, so round versus squiggly brackets for planes, square versus angular brackets for directions. And most importantly, we talked about how the symmetry of properties follows the symmetry of that lattice.